Right. Hello, guys. So we are in our third section of this chapter. Today we're gonna introduce the fundamental theorem of line integrals. So recall that previously in the last video we introduced an extension of one-dimensional integral onto a 2D curve or a 3D curve. But essentially, a curve is a one-dimensional object, so you can perform a single integral. And today we're gonna introduce sort of like a version of fundamental theorem of calculus, which actually is, and that is how we perform the same differentiation integration interplay in 2D and 3D space with respect to a single dimensional integral. Okay. And there is a lot of concept in this video, so I will break this video into two parts. Okay, so yeah, let's start with the theorem. So the fundamental theorem of line integral states that if you have a curve CT parameterized by x of t, y of t, and I want to mention that this kind of theorem also works for general 3D curve. So say you have a parameterized curve, which is continuous differentiable, meaning that your trajectory of the curve is kind of smooth, and you have a continuously differentiable function f, so that um, we are integrating the gradient. So be careful with this. Actually, sorry, let me make this more precise. No, I think that'll be good. Okay. So the statement of the theorem is that if you're integrating the gradient vector field over the curve, so don't forget about this, we have introduced two types of line integration. One is respect to the scalar function, one is respect to a vector field. For a vector field, you're taking inner product, the dot product between the vector field itself together with the tangential direction. So in this case, the fundamental theorem of line integral states that integrating over the gradient vector field over the curve actually can be computed by f of CB, where CB is obviously the endpoint of this curve, and CA is is the starting point of this curve. So it becomes f of CB minus f of CA. Or in terms of like the usual integrating notation, we can write f xy, where we plug xy to be CA and xy to be CB. So you see that this is actually a very direct generalization of one-dimensional fundamental theorem of calculus, because we're basically stating that the integration and differentiation cancels out. The only difference is that in the usual case, the differentiation is just a one-dimensional derivative, right? In this case, the so-called differentiation will be the gradient. That is the only difference. So first of all, let us prove this theorem, and let us see how this theorem actually works. So it is actually a almost one-line proof. We see that by definition, the integral over the gradient vector field on this curve C is given by definition integrating A to B gradient of f evaluated on the curve CT, taking dot product together with the tangent vector C prime of t. However, by chain rule, you can review this in, I think, section 14.4, something like that. This guy is simply this guy, right? The differentiation with respect to t of this f of x of t, y of t is actually gradient of f taking dot product together with c prime of t. So you can actually evaluate this if you want to do it term by term. Taking differentiation together with f of c of t, then you are differentiating with respect to t by f of x of t, y of t. Now by chain rule, you have partial f, partial x evaluated as c of t, taking product with x prime of t, and also the same similar term with y prime of t. And this is basically the dot product between the gradient vector field evaluated as c, taking dot product with c prime. So we see that this can be rewritten back into the differentiation of f of c of t as a one-dimensional function. And then it is fundamental theorem of calculus. So we see that taking the derivative of this guy, taking integration, is simply evaluating this guy at the starting point and at the ending point, right? So this last line is due to the usual fundamental theorem calculus because this guy is actually the antiderivative of this guy, right? By definition. Okay, so we see that in the particular case where you're integrating over a vector field, which is a gradient vector field, and don't forget that this property is called conservative vector field. If you're integrating over a conservative vector field on a curve, then you can simply evaluate it, that line integral, via plugging in the ending and starting point at the potential function f. So let us do some example. Oh, yeah, sorry. There's another remark I want to see here. So what I'm saying, if we're getting a conservative vector field, f being null blah f, meaning that the vector field is a gradient for some potential function f, then we see that by this evaluation, the consequence is that the integration, the line integral, does not depend on the path. Because you see that whatever path I put here, as long as you let those paths share the same starting and ending point, then this quantity is always the same, right? It is inconsequential of the middle part. It does not change the value, whatever it goes like this, it goes like this, it goes like that. If you share the same ending point and a starting point, then you share the same line integration. This kind of property is called the path independence. So given any path, the work done by this force is the same. This is why we call it the conservative vector field. Okay, and for now we show via this fundamental theorem of line integration that a conservative vector field has the property of path independence, meaning that the line integration does not depend on path, but only the starting and ending point. Later on, we will show that actually that is equivalent. Those are equivalent statements, meaning that every vector field with this path independency property must be conservative. And that'll be a very useful criteria. So let us go on. First, let us do some example here. So suppose this vector field f is given by 1 plus xy, e to the xy, x squared, e to the xy, j. So we suppose here that it is conservative, but when we proceed on the lecture, I think part 2, we will see how to determine whether a vector field is conservative or not. In that case, I won't give you this property. You have to find out whether it is conservative or not. So we want to evaluate this line integration over this particular curve. This is actually an ellipse, right? And we only take a quarter of it. So if you actually do the algebra and try to find out the line integration using the definition, you will see that it will be very complicated. Because, for example, if you plug in this vector field on this curve, then you'll get something like e to the cosine t sine t, which is kind of difficult to integrate in general. So this is where using the fundamental theorem of line integration comes in. First of all, we hope that because I already tell you guys that it is conservative, meaning that there is some potential function, so that the gradient of f is given by this vector field, right? So that is equivalent to saying that there is some function f, so that fx is the sky and fy is the sky, right? Actually, I don't know why I use plus here. It should be a comma. Sorry. So fx is the sky and fy is the sky. So now we want to solve for f, right? So to solve for this guy, you have to perform the, this is not a very rigorous term, a partial integration. Basically, we know that you do partial differentiation with respect to x gives you this guy. So we do integration with respect to x by considering y as a constant. So we see that fxy via this first equation should be the antiderivative of this guy respect to x, right? And yeah, you can do this like a lot of different ways. For example, the first guy here, 1 times e to the xy is simply e to the xy. But regarding y as a constant, you simply get 1 over y, e to the xy, right? The second term here, we can factor out y because it is a constant. You have x exy dx, where this is a very classical example of integrating by part, right? We set x to be u, where exy dx to be dv. In that case, du is simply dx. If you integrate over this guy, you'll get v to be exy divided by y. So we have u dv equals to uv minus v du, right? And then everything becomes quite nice. First of all, we see that this guy, after taking integration, you get exy y squared, right? Canceling this y squared together with this y, you get the same term like this with a negative sign. So actually this term and this term cancels out. And you have an extra term here, which gives us x exy. Now, usually when we're doing integration, we have to add a constant term, right? Because constant gives differentiation 0. So there is a there should be an extra constant there. However, in this case, we're doing partial integration, right? Where we're regarding y to be constant. So the so-called constant term should be anything that is a function of y. In this case, g1 of y. You can verify that actually, if you differentiate this guy with respect to x, the partial differentiation, you will get what you want. So be careful with that. That is the only difference between this type of two-dimensional partial integration in comparison to one-dimensional integration. In this case, the constant guy would be g1 of y, okay? And we can evaluate this guy again by taking integration with respect to y, and you can get simply x exy plus some constant in y, which is g2 of x. So the idea now is to compare these two formulas and see what can you choose for g1 of y and g2 of x, okay? We'll do this a lot of times later on, so this is just the first example, but that is basically how we do it. We do partial integration on those formulas, and we compare the coefficients and to see what can we choose for the extra function. In this case, this guy and this guy already look quite similar, right? So since g1 of y is equal to g2 of x, the only possibility will be an actual constant, something like 2 or 3 or 10,000, right? Because it cannot depend on y and it cannot depend on x. So it is an actual absolute constant. So we see that we have concluded that f of xy should be x e to the xy plus c, where c is an actual constant, okay? In this case, g1 of y and g2 of x are just c. There is a possible scenario where g2 of x, for example, if you integrate this guy and you get x exy plus say x squared plus g1 of y, then in that case, this g2 of x will be x squared, right? So that depends on the situation. In this case, it is very nice because both formula coincide. So the constant term is actually an absolute constant, a real number, not a function. We will see more example afterwards anyway. So, but now we have the potential function. We know what thing take gradient will be f. Then you can do your line integration via the fundamental theorem of calculus, fundamental theorem of line integration. The integration over a gradient vector field is simply that potential function evaluated at an endpoint and a start point, and we subtract those guys. In this case, the endpoint will be c of power over 2, and the starting point will be c of 0. So c of power over 2 in this case will simply be 0, 2, right? And c of 0 will simply be 1, 0. So you have f of 0, 2 minus f of 1, 0, and it should be minus 1. So you can see that instead of actually doing the integration, what we do is sort of like we trace back the so-called antiderivative of this vector field f in terms of a function. So we are again trying to find some anti-differentiation. And then we simply evaluate the anti-differentiation at the boundary point. And that will be our corresponding line integration, a definite integral, basically. All right. So that is the first example. And it sort of kind of shows you how strong this theorem is, no matter how easy the proof seems to be. You can actually try to compute the line integration of this guy using definition. You will see it is extremely hard, and it will be kind of difficult to put everything together. So it is very nice if you can evaluate the potential and simply evaluate everything in the potential. Okay, so now one sort of a natural question is that when can you decide under what circumstance will a vector field F be a conservative vector field or not? We have seen in our last video that there is some vector field which is not conservative, meaning that not all vector field can be written down as a gradient. That is why we need to provide some useful criteria to show that a vector field is conservative or not. We have shown a necessary condition last time, which is when a vector field F is conservative, then the P and Q satisfy some condition, right? The PQR or PQ. But that is not really enough because we need a sufficient condition, meaning that you need to have some criteria to show that if we verify this, this, and this, then the vector field F will be conservative. And that is what we're going to do today and the next lecture. So before doing so, everything actually has something to do with the domain, the place where the vector field is defined. So let us first define some terminology for the domain. This will not be crucially important. As I mentioned in the first class, the important part about this lecture is the computational aspect. The theoretical aspect is also a very good way to familiarize yourself with computation. It won't be required in your exams, obviously, for proofs and this definitions. But yeah, just for completeness, I will include everything here. So this theorem actually works for general domain. So let me put some omega. Let me put some omega inside Rn. In most cases, n is just 2 and 3. So in either Cartesian plane or 3D Cartesian coordinate space. So we mentioned that omega is said to be open. That is a adjective, open set. The set is said to be open if for every x belongs to omega, so for every point, there is some small r, some radius r, so that the ball centering at x with radius r, which is simply defined as this guy, right? We collect every y so that the distance between y and x are less than r. This is a ball centering at x with radius r, so that this ball belongs to omega. So basically, an open set is that whatever point you choose inside that open set, you can always have a ball which is small enough that is contained in omega itself. So that seems like a natural property, right? So like what set are not open? For example, a closed set is not open. So I'm not sure. I think I have defined closed sets somewhere before. I think it's back in maybe extreme value theorem. So you can go back there. I think it's in section 14.7 on the maximum and minimum. So closed set basically tells you that you contain the boundary. An open set is something like it does not contain a boundary. So for example, if we're dealing with a rectangular set, say AB times CD, like this. Okay. This boundary is exactly why it is not open. Because, for example, if you choose a point on a boundary, then whatever ball you choose, you always have some point that lies outside the set, right? In this case, this part. And this does not depend on radius. For every radius, for how small radius is, you will still have some point that is outside the set, right? That is why boundary matters. In this case, boundary actually tells you that this set is not open. So any set that does not contain its boundary is actually open because for any point which is not on a boundary, you can choose something small, so small, so that the ball is contained in the set itself. So basically, that is what open means. Open set means that the set does not contain its own boundary. Okay, and open set is usually the nicest set to work with because you have so many space between yourself and the boundary. Boundary always gives some difficult calculations. All right. The second property I want to introduce here is called path connected. This is more direct than the last property. So basically, a set omega in Rn is path connected when every 2 points in omega can be joined by a path. So for example, these two are connected, or path connected basically. Strictly speaking, there's a difference between path connected and connected in mathematical terms, but in this case, I'll just put them together because we won't be dealing with so many mathematical terminology and proofs. So in this case, let us just call it connected. So you see that these two guys are connected because for every 2 points, you can always find a line to connect them, right? This set is in particular not connected. This obviously this itself is connected, but this together is not connected. For example, some points here and some points here cannot be connected to some line that is within the omega. There's obviously some line because R is connected, so you can always choose some line, but this line will not be inside omega, right? So basically, connected set or path connected set is set that 2 points can be joined within the omega. Okay, so maybe I should emphasize here. It can be joined by a path in omega. Let me emphasize that. In omega. Okay, so basically the set is intuitively connected. You don't have anything which is on the exterior. There's nothing isolated, basically. Okay, this dash property, we'll not use this today, but I will first give the definition. We'll use this heavily next time. And it is kind of scary to see the definition here, but actually it is kind of intuitive to some degree. So let me first introduce this definition. We say a connected set is, with a stronger formulation, simply connected. So basically, when we say something is simply connected, we assume that it's connected. This is a stronger property than connectiveness. So we say set omega is simply connected whenever for any two paths, in this case C0 and C1, let me just define it on 0, 1. You can define it on 0, 2, 0, 3, 1, and 2. It's always okay. In this case, I just use 0, 1 for convenience. For any two paths with the same starting point and ending point, you can always find a so-called homotopy between those two paths. So before I define this homology mathematically, I want to show the graph here because intuitive is more important. So we see that we have a orange line here, which is C0, and we have a blue line here, which is C1. So for homotopy basically in intuitively speaking is a way to translate this orange line towards this blue line. So homotopy is basically a collection of lines that is within these two guys that you can go smoothly from this orange curve towards this blue curve. For example, in the easiest case where we're dealing with a circle, and this is C0, and this is C1. Then you can do something like flattening down the curve, right? This is C0, and you can flat down, flat down, flat down, flat down, and it goes toward another side. And you can get another curve, C1. So that is what homotopy means. Homotopy basically means how you can transfer from a curve to a bunch of curves and smooth out to C1. So those two curves are homotopy, meaning that you can do such transformation between those two curves. And that kind of definition leads to this mathematical formulation. So basically a homotopy means that you have a map H that goes from 0, 1, 0, 1. So that means that you have two variables towards omega, so that the following property holds. We see that the first condition is that HT0 is C0 T. That basically means that, so maybe let me do the terminology first. This first variable T here encodes the timing. So basically, for T encodes where the curve goes. For example, this is the same T. And the S here encodes the path. So for example, when S is 0, we see here that it is simply the C0 curve. And when S is 1, it simply is the C1 curve. So we see here that, for example, this will be C0, which is HT of 0. I forget the arrow here. HT of 0. And you can do that sort of perturbation to see that this is HT 0.1, maybe HT 0.5, maybe HT 0.9, and all the way down back to HT1, right? So the second parameter is simply a enumeration of the paths. Only that in this case, the enumeration is continuous. We have all the way from 0 to 1. And the second property is more easy to understand. We have H0 S to be C0 naught or C1 naught. Basically, that is saying that for any path, this means that any path, right? For any path, the starting point is always the same. It always is here. And similarly, the ending point is always the same. So fixing the first variable is saying some property that is general about all paths. Fixing the latter variable is saying some property about that particular path. So you can see that in this case, we're saying that the first path is C0 and the last path is C1, where these paths share the same starting point and ending points. Okay? So basically, this property tells you this, that. I hope that this is kind of intuitive, because I would say that if you understand this guy, then this two just comes in very naturally, right? So just to say again, if any two paths share this kind of, any two paths with the same starting and ending point share this homotopy relationship, then we say that this connected set omega is called simply connected. So again, let us look at what happens if we're not simply connected. For instance, this guy with the hole is not simply connected. You see that these two paths shares the same starting and ending point, right? However, there is no homotopy between them, because you cannot actually do a continuous transformation between these two guys. Any path that that goes from this guy to this guy has to go like either this or this, right? It has to go around the circle. So you cannot continuously transfigure the C0 towards the C1. There will be some gap between these two guys, obviously. So basically, to some degree, you can sort of understand this simply connected property to be that this set does not have any hole. In some sense, there's no hole. Okay. So let us go back to what we have defined now. We have defined three different properties. One is openness, one is connectivity, and one is simply connectivity. So open means that the set does not contain its boundary. Basically, there's no boundary. And being connected means that you can join any two points with the path inside the set itself. Being simply connected essentially means that you don't have any holes. And mathematically, it means that you can transfigure two curves with the same ending and starting points together with each other. So I hope this is a sufficiently nice examples to show what is open, what is not open, what is connected, what is not connected, and what is simply connected by what is simply connected. Okay. Right. So it boils down to our first big theorem today, which is what I just mentioned before. We already showed that fundamental theorem of line integration entails the path independency of gradient vector field, right? Or conservative vector field. In this case, we will show that it is equivalent, meaning that any path independence vector field is actually conservative. So let me say the theorem. In this case, we suppose omega is a connected open set, so you don't have boundary, and every 2 points can be joined by a curve inside omega. And we have a vector field. In this case, you can suppose up to Rn. So basically, for a planar vector field or a spatial vector field, this theorem works. Then the following statements are all equivalent, meaning that they can imply one another. The first statement is that f is conservative in omega. Don't forget that this basically means that f is equal to gradient f for some potential function inside omega. That is the definition. And the second property is that the line integral over a vector field over any simple closed curve is always zero. So let us sort of recall this terminology. Simple basically means that your curve does not have any intersection. And closed basically means that you have a same starting and ending point. So it looks like a loop like this. This will be a simple closed curve. So the second property claims that this vector field always vanish, the line integral of this vector field always vanish on closed curve. So in terms of physics, that means that if you're going respect to a loop, then it does not have any work to do. That conservative vector field, conservative force, does not perform any work to the particle. The third property is what we just mentioned, the path independency. So it says that the line integral of this vector field over C1 and C2 are always the same as long as C1 and C2 shares the same starting and ending points. Okay, so these are three different properties from a vector field, and we will now show that it is equivalent. Mathematically speaking, usually when we're proving this equivalent type of statement, we usually prove in this way. we prove that 1 implies 2, and 2 implies 3, and 3 implies 1. In that case, any of the one of these three items implies one another, right? And that is a more efficient way to prove this. We don't like to prove 1 to 2 and 2 to 1, 2 to 3 and 3 to 1, and all the way like that, because there's too many things to prove. So a nice path to follow would be 1 to 2, 2 to 3, and 3 to 1. So first of all, 1 to actually follows directly from fundamental theorem of line integration, because we know that as long as f is conservative, f is equal to some gradient of f, right? So let me mention that here. Suppose we write f, the vector field, to be the gradient of f. Then by the fundamental theorem of line integration, we know that the line integral of this vector field over this simple closed curve is given by f of ending point minus f of starting point. However, in this case, this is a closed loop, right? The point is closed. So the starting point is actually ending point, meaning that these two guys are actually the same point. And obviously they share the same function value, so it'll be 0. Okay? So very intuitively, a conservative vector field should have line integral to be 0 whenever the curve itself is closed. Simply closed, basically, same point closed. Okay. The second item here is showing that the property 2 implies property 3, meaning that if you have this property that line integration over a closed curve is 0, then we have path independency. And it is actually, again, very simple, because we're now integrating C1 and C2, right? However, if you join C1 and minus C2, meaning that we're going backwards in C2, we see that C1 in this case is this, C2 in this case is this. They share the same ending and starting point. However, minus C2 goes from the ending point of C1 towards the starting point of C1, right? So C1 taking union with minus C2 is actually a closed curve, right? So let me emphasize this again, because C1 and C2 share the same starting and ending point. So C1 union minus C2 will be a closed simple curve. So we know that by the property 2, that 0 is equal, by property 2, we know that any integral over a closed simple curve is 0, right? That is definition. That is the assumption of property 2. And C itself is simply C1 union minus C2, right? And by property of line integration, if you're integrating over several pieces of line integral, then you're simply doing it along this plus something along this, right? In this case, it is C1 and minus C2. And we learned last time that if you're going in the opposite orientation, then integration over minus C2 is simply integration over C2 together with a minus sign. So you have a minus sign here. So we see that actually the integral over C1 is equal to the integral over C2 because this thing is equal to 0. So actually the equivalence between 2 and 3 is very obvious, because if you have a 0 integration over a curve, then obviously this and this integral has to be the same. And conversely, if this and this has to be the same, then you must have integration 0 on the curve, right? On a closed curve, sorry. So I hope this diagram is sufficiently enough for you guys to understand. Basically, you have path independency whenever you have this closed curve property, okay? Right. The essence of this theorem is actually how we can prove conservativity of a vector field by path independency. And this is actually a very elegant proof. So let me provide that now. So the idea now is that we want to prove f is conservative, meaning that we want to find some function f, which is called a potential for this capital F, right? Basically, we want to show that there is some function f so that capital F is equal to gradient f, right? That is the idea. So now, first of all, let us try to define this f. And it's actually quite intuitive to some degree. We want to find the antiderivative of this capital F, right? So the method is doing integration. In this case, line integral. So first of all, let us fix any point. This AB can be actually arbitrary. And since omega is path connected, we know that there is always a path joining AB to XY for every XY belongs to omega, right? For example, if we're dealing with this guy, then we cannot perform this curve because if we choose AB somewhere here, then anywhere here xy cannot be connected to that AB. So connectivity for now is kind of important. So for the existence of this type of path connectivity, we can perform the following definition. We define the function f from omega to r defined by the integration line integral over this vector field itself together on the path from AB to xy. So this definition does not make any sense in general because for different paths, you might have different line integrals, right? However, for now, we're proving the property 3 implies property 1, right? Property 3 tells us that actually there's the path itself does not really mean anything. The only thing important is the starting point and the ending point. So this definition actually makes sense under the assumption of 3 because we know that only thing matters is the point AB and the point XY. So merely the existence of this path will be sufficient. We know that there is some path that tracks from AB all the way to XY. And any other path actually shares the same line integration for with respect to that path. So this will be a well-defined function, okay? F of xy to be any path, any line integration over the path from AB to xy. In this case, AB is not the point. AB is just some point. All right. Now we have now a function f, right? This should be a candidate for our potential function. So the task now is to differentiate this function and see whether the gradient of this f is actually capital F. Okay. So let us try to evaluate the differentiation at x0, y0. Now we already used the path connectivity, right? Now we use the openness. So since omega is an open set, for this particular point x0, y0, you can always choose a small ball, small enough ball. In this case, radius is h, so that the ball with center at x0, y0, with radius h, actually is contained in omega, right? And why is that useful? Because a ball is a very nice thing that we can treat. In general, omega might look very strange, but we know how a ball looks like, right? That is why openness is kind of very useful because it tells you that we can shrink what we want to consider to a very regular space that we already know the properties. For example, square or a circle. In this case, a circle. So let us choose the path D to this I denote by D arrow. So let us denote the path from AB to x0, y0 by D. And again, the existence of this path follows from path connectivity. And let us choose the path from AB towards x0 plus h and y0 to be D union with C, where C is a horizontal curve. So C basically goes from x0, y0 to x0 plus h, y0 via increasing x0. It is a straight line. And as we said, the choice of path does not really matter. That is a very big crucial point to mention. So now we choose the path like this and like this. And let us start computing the differentiation. So the difference between f of x0 plus h minus f of x0 by definition is the integration over d and c f ds. This whole guy is this guy, right? We're integrating over every path from AB towards x0 plus h, y0. In this case, d union c. And we're subtracting fx0, y0. So in this case, it is integration over d. And then we know that you're integrating over the joint curve, right? So the line integral is simply integration over d and integration over c, where the d part actually cancels out with this guy. So the remaining guy is the integral over c. So let us stop here and let us go back on what we're doing. So the idea is to evaluate the differentiation of this potential function and show that it is actually vector field capital F. Now we have already showed that the difference between the function here is actually given by a line integral on this small path C, which is a horizontal integration. Now, actually let me mention here, if we set F itself to be PQ, again, the whole thing here actually works for n-dimensional. I just use two-dimensional to be to lighten on the notation. So if we denote F to be PQ, then what is this by definition? So then let us first parameterize this CT. CT is actually really simple, right? It is just x naught plus TH and y naught, where t goes from 0, which is this point, to 1, which is this point. So let us evaluate this line integration. We're simply plugging in f to x naught plus TH y naught, and we multiply c prime of t, right? But in this case, c prime of t is simply h0, right? There's no difference in the y direction. So you have h0 and p of c of t and q of c of t, where this guy just vanishes out. Now, let us actually do the partial differentiation. So we have already the difference here be given by this guy here, right? So let us write it down. And we also divided by h, right? This whole thing is definition of partial differentiation. So we have now h to be cancels out, this h here and this h here cancels out, and the only remaining term is this integration over t. However, we know by the mean value theorem for integration, meaning that for every continuous function g of x, if we're integrating over the interval a to b, then you can find some c so that it is equal to g of c b minus a. And just to mention, in this case, g of c is called the average value of g on this domain AB. So you can find some point t, or actually just some point between x naught and x naught plus h, that is denoted by xh, to so that this whole integral is equal to some function value. There's actually a 1 minus 0 here, but 1 minus 0 is just 1, so that does not really matter. Why is this useful? Because we see that when h goes to 0, then x naught plus h actually strings together, right? So this xh actually converges to x naught when h goes to 0. And since p is assumed to be a continuous function, so we have this be equal to p of x naught y naught. This is exactly what we want, because we want the partial differentiation with respect to the first variable to be the first function in capital F, right? So that is kind of go through this again. The difficult part about this theorem is to proving the path independency implies conservativity. And the idea that we are trying to use is that we created a very nice function based on path independency, which is the line integration from any point AB. This is not important. We can see that in the proof towards the point xy of this vector field capital F. And we want to show that the gradient of F is actually capital F, right? So the difference I'm computing here is due to the fact that I want to estimate this limit. And we now have already derived that this difference is given by some integration over t, where we have it divided by h again to show the difference quotient actually converges to what we desire. And we see in this case, it does converge to p of x naught y naught, which is what we want. The same thing happens for the y coordinate. You can show that, actually try to do that by yourself. Fy x naught y naught is given by q x naught y naught. So that is basically showing that capital F is equal to the gradient of little f here, meaning that this is actually a valid potential. So we see that in fact, path independency shows you that you can create the potential itself. And it looks like this, okay? Right, so again, that does try to encode this theorem in your brain. Basically, we're showing some equivalent formulation for conservativity. Conservativity itself is a kind of a difficult condition to manage, because it says that there exists some function f so that the gradient f is capital F. But this kind of statement is not really practical, because the existence does not really guarantee you anything. If you, in that case, if you want to show a vector field is conservative, you have to find that finite potential function f, right? If you want to show that it is not conservative, then you have to prove that there is no such f, right? So no such potential function. So that in general would be a very hard task to do. But now for this second and third equivalent formulation, we can actually have a really nice, clear idea on this conservativity, because if you want to show that f is conservative, then you can evaluate the line integration on a closed curve and to see whether it is zero or not. If it is zero, for every curve, then it is indeed conservative. If there is some curve so that the line integration is non-zero, then f is not conservative. Okay, so that comes to this example here. Let me do this. So in this case, I ask you to show that this vector field is not conservative. So it is given by y and x squared y, where in general we denote the first component by p and the second one by q. So in this case, I already claimed that it is non-conservative. So the thing you want to do is to evaluate, for example, this guy on two different curves, and they should give different values. Or you can compute this guy on a closed curve and show that it is non-zero. In this case, just for convenience, I choose the square from 0, 0 to 1, 0, and all the way like this. So the integral of f over ds is given by the summation over these four different integrals. Here, here, and here, and here. And then by definition, the first guy, f here on C1, can be parameterized by T0, right? T and 0, where T goes from 0 to 1. And since there is no y change, so dy is 0, meaning that you only consider dx, which is dt, because x of t is t, so dx is dt. And similar things holds for the rest of the term. This is q because there is no changing in x. This is p because there is no changing in y, and so on and so forth. So after the evaluation, you can see that the term is minus half, which means that this particular vector field, there exists a closed curve so that the line integral is not zero. But based on our previous theorem, we know that if you're conservative, then you must have line integral to be vanishing on a closed curve. So this guy must not be a conservative vector field. Okay. Now, as I mentioned, we see that this is actually already a very powerful theorem, but there is a difficult task here. Let me try to formulate this. It will now be kind of simple to prove that a vector field is not conservative because it only requires you to find a path which is closed so that the line integral does not vanish. However, to show that f is conservative, you have to show that for every simple curve, it actually gives you line integral 0, which is in some sense not possible for human being. You cannot exhaust every simple closed curve, right? So there should be a more practical way to do this, and there is indeed. So we will talk about this next lecture because the proof is a little bit difficult. This is called Poincaré's theorem. Poincaré is a great mathematician back in the day, and it shows that under certain conditions, you can actually perform a really simple algebraic criteria for conservative vector field, which is what we mentioned last time. We mentioned last time that if f is conservative, and suppose f is a two-dimensional vector field, then it must satisfy this equation for q and p. And this means that this condition is necessary, right? In this case, we will show that it is actually sufficient, meaning that as long as this guy holds, then you have conservativity under some condition, basically. But this is way better than what we have done before, right? Because this is actually a verifiable computation. You don't have to choose like 10 million different paths and you still cannot prove conservativity. In this case, you simply want to evaluate the differentiation for the components of the vector field. So let us go back on what we had learned in this lecture. First of all, we have done this very naive fundamental theorem of line integral, showing that the integration over a gradient vector field along a curve is always given by the difference between the potential function evaluated on starting and ending points, which looks very much like the ordinary one-dimensional fundamental theorem of calculus. And basically, the previous theorem entails that the gradient vector field have the nice property that it should be path independence. Two paths give you the same line integral. Or in some sense, you can say that every closed curve gives you vanishing line integral. And in this part of the lecture, we prove that as long as your set is nice enough, it is connected and open, then this f is conservative on omega, or basically saying that f is a gradient vector field if and only if it satisfies the path independent property. And we will start from this base point to prove the well-known Pocahontas theorem next lecture. Okay. So that is all for this course. I will see you in the next in part 2. See you.